Hello, and welcome to the Nocturnal Astronomer. I'm your host, Atlas Reid, and tonight we're embarking on a gentle voyage through our cosmic home, the Milky Way galaxy. We'll drift through spiraling arms of stars, float past nebulae where new suns are born, and contemplate the quiet majesty of our galactic neighborhood. Think of this as a slow, peaceful tour through the greatest structure humanity has ever known, a place so vast that light itself takes 100,000 years to cross from one side to the other. If you enjoy these explorations of the cosmos, I'd love it if you could give this video a thumbs up and subscribe to the channel. It helps other stargazers find these relaxing journeys through space. And I'm curious, where are you watching from right now, and what time is it where you are? Drop a comment and let me know. Perhaps you're watching as the sun sets, or maybe it's the middle of the night and you're letting the universe lull you to sleep. Let's dive in. The Milky Way is a barred spiral galaxy, which means it has long arms that curve outward from a central bar of stars. Imagine looking down at a whirlpool in water, with streams spiraling outward from the center. That's roughly what our galaxy would look like if you could step outside it and take a photograph. Of course, no human has ever seen the Milky Way from the outside. We're embedded within it, like someone trying to understand the layout of a forest while standing among the trees. Our solar system resides in what astronomers call the Orion Arm, sometimes referred to as the Orion Spur. This is a minor arm, a smaller branch between two of the major spiral arms. We're located about 26,000 light years from the galactic center. To put that in perspective, if you could travel at the speed of light, which is 186,000 miles per second, it would still take you 26,000 years to reach the heart of our galaxy. We orbit around this center at roughly 500,000 miles per hour, yet it takes us about 230 million years to complete just one orbit. The last time our solar system was in this exact position, dinosaurs had not yet appeared on Earth. The Milky Way contains somewhere between 100 billion and 400 billion stars. The uncertainty in that number reflects just how difficult it is to count stars when you're inside the galaxy, surrounded by dust and gas that block our view in many directions. Some of these stars are larger than our sun, some smaller. Some burn hot and blue, others glow cool and red. Each one is a nuclear furnace, fusing hydrogen into helium and releasing energy that has traveled across the galaxy to reach our eyes. Between the stars lies the interstellar medium, a thin soup of gas and dust. This material is so diffuse that it would count as a vacuum by Earth standards, yet it plays a crucial role in the galaxy's life cycle. Stars are born from clouds of this material, and when stars die, they return enriched gas and dust back to space, seeding the next generation of stars with heavier elements. Our own sun is a third-generation star, meaning it formed from material that had already been through at least two previous cycles of stellar birth and death. The disk of the Milky Way, where most of the stars reside, is incredibly thin relative to its diameter. If you shrunk the galaxy down to the size of a pancake, it would be thinner than an actual pancake. This disk is about 1,000 light years thick, while its diameter spans 100,000 light years. Our sun bobs gently up and down through this disk as we orbit, like a horse on a carousel that also moves in a wave-like pattern. At the heart of the Milky Way lies something extraordinary. For decades, astronomers observed stars near the galactic center moving at tremendous speeds, orbiting around what appeared to be nothing. One star, known as S2, completes an orbit in just 16 years, reaching speeds of up to 3% the speed of light. For a star to move that quickly, it must be orbiting something with an enormous gravitational pull, something with a mass millions of times greater than our sun, compressed into a relatively small region of space. That something is Sagittarius A star, a supermassive black hole. In 2022, astronomers finally captured an image of the glowing ring of material around this black hole, confirming what scientists had long suspected. Sagittarius A star has a mass equivalent to about 4 million suns, yet the black hole itself, the region from which not even light can escape, is only about 17 times the diameter of our sun. If you replaced our sun with Sagittarius A star, the event horizon would fit comfortably within the orbit of Mercury. Black holes are perhaps the most misunderstood phenomena in space. They're often portrayed as cosmic vacuum cleaners, sucking up everything around them. In reality, black holes obey the same laws of gravity as any other massive thing. If you replaced the sun with a black hole of equal mass, Earth would continue orbiting exactly as it does now. We wouldn't be pulled in. Of course, we'd freeze without the sun's warmth, but that's a different problem. The danger of a black hole comes from getting too close, where the gravitational pull becomes so intense that not even light can achieve escape velocity. The region around Sagittarius A star is not quiet. Gas and dust fall toward the black hole, forming an accretion disk, a swirling structure where material heats up due to friction and gravitational compression. This material can reach temperatures of millions of degrees, hot enough to emit X-rays and other high-energy radiation. Occasionally, the black hole has a feeding event, consuming a clump of material and briefly brightening in X-ray emissions. Surrounding the galactic center is a bulge, a roughly spherical collection of stars that extends several thousand light years in all directions. This bulge contains some of the oldest stars in the galaxy, ancient suns that formed when the Milky Way itself was young. The stars here are packed more closely together than in the spiral arms. If Earth orbited a star in the galactic bulge, our night sky would be spectacular, filled with brilliant stars so numerous and close that there would hardly be any darkness between them. The bar structure that defines our galaxy extends through this bulge. The bar is thought to form through gravitational interactions among stars and gas, and it plays a role in funneling material toward the center, feeding the black hole and triggering bursts of star formation in the inner regions of the galaxy. The spiral arms of the Milky Way are not solid structures. They're better understood as density waves, regions where stars and gas temporarily crowd together. Think of traffic on a highway. Sometimes cars bunch up, creating a slow-moving area, even though individual cars pass through it. The spiral arms work similarly. Stars move in and out of the arms as they orbit the galaxy, but the arms themselves persist as regions of higher density. These arms are sites of intense star formation. The Perseus arm, the Scutum Centaurus arm, and the Sagittarius arm are the major structures, each containing countless stellar nurseries. When you look at images of the Milky Way spiral arms, the bright blue regions you see are clusters of young, hot stars. These massive stars burn brilliantly but briefly, living only a few million years before exhausting their fuel and ending their days in spectacular supernova explosions. Star formation begins in giant molecular clouds, vast structures of gas and dust that can span hundreds of light years. These clouds are cold, just a few degrees above absolute zero, and dark, obscuring the light from stars behind them. The Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion, is one of the closest stellar nurseries to Earth, about 1,300 light-years away. Within its glowing gas, dozens of new stars are being born right now. The process of star formation starts when a region within a molecular cloud begins to collapse under its own gravity. This can be triggered by a nearby supernova shockwave or simply by random fluctuations in density. As the cloud collapses, it breaks into smaller clumps, each of which will potentially become a star. The collapsing material heats up, and at the center, temperatures and pressures eventually become high enough to ignite nuclear fusion. A star is born. Young stars are often surrounded by a disk of leftover material. This protoplanetary disk is where planets form. Dust grains stick together, forming larger and larger clumps, eventually building up into asteroids and then planets. Our own solar system formed this way 4.6 billion years ago from a cloud of gas and dust in one of the Milky Way's spiral arms. The most massive stars in these nurseries, those with dozens of times the mass of our Sun, emit intense ultraviolet radiation. This radiation ionizes the surrounding gas, causing it to glow. That's what creates the beautiful colors we see in nebulae. Red hues come from hydrogen, green from oxygen, blue from regions where stars heat the gas to extreme temperatures. These colors are real, though often enhanced in astronomical images to bring out details invisible to the human eye. The Milky Way stars are not all the same age. Astronomers categorize them into populations based on when they formed and what elements they contain. Population 1 stars are young, rich in heavy elements, and found primarily in the spiral arms and galactic disk. Our Sun is a population 1 star, formed relatively recently in cosmic terms, from material that already contained carbon, oxygen, iron, and other elements heavier than hydrogen and helium. Population 2 stars are older, with very few heavy elements. They're found primarily in the galactic halo, a roughly spherical region surrounding the disk, and in globular clusters. Globular clusters are dense, spherical collections of stars, some containing hundreds of thousands of suns packed into a region only tens of light years across. The Milky Way has about 150 known globular clusters, most of them orbiting in the halo. These ancient clusters formed when the galaxy was young, more than 10 billion years ago. At that time, the universe contained almost no elements heavier than helium. The first generation of stars, population 3 stars, had to form from pure hydrogen and helium. These primordial stars were likely enormous, hundreds of times the mass of our Sun. They burned quickly and died in powerful supernovae, scattering the first heavy elements into space. No population 3 stars have ever been observed. They all died long ago. But their legacy is the enriched material from which all subsequent stars formed. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood was forged in the core of a star or in the explosion that ended its existence. Stars are element factories. In their cores, nuclear fusion builds progressively heavier elements. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, and so on, up to iron. Elements heavier than iron, like gold and uranium, are created in supernova explosions or in collisions between neutron stars. The Milky Way has witnessed countless such explosions. Supernovae are rare in any given region, occurring perhaps once per century in a galaxy like ours. But over billions of years, the cumulative effect has been to enrich the galaxy with a full periodic table of elements. The iron in Earth's core, the calcium in your bones, the gold in any jewelry you might wear, all of it was created in stellar furnaces and scattered into space by dying stars. The disk of the Milky Way also has a significant population of white dwarf stars, the dense remnants left behind when stars like our Sun exhaust their nuclear fuel. A white dwarf packs roughly the mass of the Sun into a sphere about the size of Earth. With no fusion occurring, a white dwarf simply cools over billions of years, fading from white to yellow to red to black. The oldest white dwarfs in our galaxy are so cool they're nearly invisible, dark embers of stars that burned when the universe was young. Beyond the visible disk of the Milky Way lies the galactic halo, a sparse region extending perhaps 300,000 light-years from the center. The halo contains globular clusters, ancient stars, and something far more mysterious. Most of the halo's mass is dark matter, an invisible substance that reveals its presence only through its gravitational influence. Dark matter does not emit, absorb, or reflect light. We cannot see it directly. Yet without it, galaxies like the Milky Way would not exist. The visible matter, stars and gas, does not have enough mass to hold a galaxy together with the rotation speeds we observe. Stars in the outer regions of the Milky Way orbit much faster than they should if only the visible matter were providing the gravity. Something else, something with mass but no light, must be there. This invisible component is what astronomers call dark matter. It's thought to make up about 85% of the matter in the universe. Despite decades of searching, we still don't know what dark matter is made of. Leading theories suggest it might be composed of exotic particles that barely interact with normal matter, passing through us and the Earth without any effect. Experiments around the world are trying to detect these particles directly, but so far, dark matter remains one of the great unsolved mysteries of physics. The halo is also home to the Milky Way's satellite galaxies, smaller galaxies bound by gravity to our own. The two most prominent are the Large and Small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches in the night sky. These dwarf galaxies orbit the Milky Way, and over hundreds of millions of years, their interactions with our galaxy create streams of stars and gas that crisscross the halo. Recent surveys have discovered dozens of these satellite galaxies, most of them so faint they were unknown until advanced telescopes could detect them. Some are tiny, containing only a few thousand stars, making them more like oversized star clusters than true galaxies. The gravitational tug-of-war between the Milky Way and these satellites is gradually pulling them apart. Eventually, they will be absorbed completely, their stars becoming part of the Milky Way's halo. In fact, much of the Milky Way's halo appears to be built from the remnants of smaller galaxies that merged with ours billions of years ago. Astronomers can identify streams of stars that share common motions and compositions, revealing their origin as ancient dwarf galaxies. This process of galactic cannibalism is a fundamental aspect of how large galaxies grow. The Milky Way has been absorbing smaller galaxies throughout its history, and it will continue to do so. The Milky Way is not isolated. It's part of a group of galaxies called the Local Group, which contains about 80 known galaxies spread across a region roughly 10 million light-years in diameter. The largest members are the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. Andromeda is the nearest large spiral galaxy to us, about 2.5 million light-years away. Andromeda is also heading toward us. Measurements of its motion show that in about 4 billion years, the two galaxies will collide. Galaxy collisions sound violent, but they're surprisingly gentle. Galaxies are mostly empty space. The distances between stars are so vast that when two galaxies merge, individual stars almost never actually collide. Instead, they pass by each other like two swarms of fireflies intermingling. However, the gravitational interactions during the collision will be dramatic. Stars will be flung into new orbits. Some will be ejected from the merged galaxy entirely, cast out into intergalactic space. The gas and dust in both galaxies will collide, and these collisions will trigger enormous waves of new star formation. For a period of perhaps a billion years, the merged system will blaze with the light of newly born stars. The supermassive black holes at the centers of both galaxies will eventually merge as well. As they spiral toward each other, they will emit gravitational waves, ripples in the fabric of space-time itself. These waves will carry away energy, causing the black holes to draw closer until finally they unite into a single, even more massive black hole. This merger will be one of the most energetic events in the local universe, though by the time it happens, humanity will either be long extinct or evolved into something unrecognizable. After the collision, the Milky Way and Andromeda will no longer exist as distinct entities. They will have formed a new galaxy, an elliptical or perhaps a peculiar galaxy, depending on the details of the merger. The spiral arms will be disrupted, and the orderly rotation of the disk will give way to a more random distribution of stellar orbits. Our Sun, if it still exists, will likely be in a very different part of this new galaxy than it is now. But 4 billion years is a long time. Our Sun will be nearing the end of its main sequence lifetime. In about 5 billion years, it will exhaust the hydrogen in its core and begin fusing helium, swelling into a red giant. Earth will likely be engulfed. Whether or not any remnant of human civilization will still exist to witness the collision with Andromeda is impossible to say. The Milky Way is more than just a collection of stars. It's a dynamic, evolving system with a rich history stretching back over 13 billion years. It's a place where matter cycles through generations of stars, where black holes lurk at the center, where new worlds are constantly being born in glowing nebulae. It's also our home, the only galaxy we'll ever truly know from the inside. When you look up at the night sky on a clear, dark night, away from city lights, you can see the Milky Way as a band of soft light stretching across the heavens. That band is the combined light of billions of distant stars, too faint to see individually, blending together into a river of light. Ancient cultures around the world told stories about this celestial river. The Greeks saw it as milk spilled by the goddess Hera. Norse mythology described it as the path to Valhalla. Australian Aboriginal peoples saw it as a river or a road. It wasn't until the early 1600s that Galileo turned his telescope to the Milky Way and resolved it into individual stars. This was a profound discovery. The hazy band was not some celestial fluid or pathway. It was stars, countless stars, too distant and dim to distinguish with the naked eye. This realization was one of the first hints that the universe is far larger and more complex than it appears. Today, we understand the Milky Way in exquisite detail, though mysteries remain. We know its shape, its size, its rotation rate. We know where stars are born and how they die. We know about the supermassive black hole at its heart and the invisible dark matter that holds it together. Yet there is still so much to learn. New discoveries are made constantly. New stars are found, new structures in the galactic halo, new insights into the processes that govern galaxy evolution. The Milky Way is also a reminder of our cosmic context. We are creatures of this galaxy, born from material forged in its stars, living on a planet that circles one of those stars. Our lives are brief compared to the timescales of the galaxy, yet we are part of its story. Every thought you think, every breath you take, is an expression of the galaxy's matter organizing itself into complexity. Perhaps the most humbling aspect of studying the Milky Way is realizing how little of it we can ever hope to explore. At current technology levels, it takes decades just to send a probe to the outer edge of our solar system. The nearest star, Proxima Centauri, is 4.2 light-years away. With present-day spacecraft, it would take tens of thousands of years to get there. The scale of the galaxy is so immense that human exploration beyond our immediate solar neighborhood seems impossible unless future civilizations develop technologies we can barely imagine. And yet, we can explore the Milky Way with our telescopes and our minds. We can study the light from distant stars, decode the messages carried by that light, and piece together the story of our galaxy. We can stand on our small planet and reach out with instruments and mathematics to understand structures hundreds of thousands of light years away. That is, in its own way, a kind of exploration. We may never walk on the surface of a planet orbiting a star in the galactic bulge, but we can know that such planets exist, we can understand the environment they inhabit, and we can imagine what it might be like to look up at their night sky. The Milky Way will outlive our sun, outlive Earth, outlive any trace of humanity. Billions of years from now, long after the sun has faded to a white dwarf and cooled to darkness, the galaxy will continue its slow rotation. New stars will be born, old stars will die, and the great cosmic cycle will go on. In some distant future, perhaps another species will look up at their night sky, see the band of light we call the Milky Way, and wonder, just as we do, about their place in this vast and ancient structure. Between the stars of the Milky Way exists a realm that is neither empty nor full, a space where matter exists in its most diffuse form. This is the interstellar medium, the gas and dust that fills the gaps between stellar systems. Though it seems like nothingness compared to the density of planets or stars, this tenuous material is absolutely essential to the life cycle of our galaxy. Without it, no new stars could form, and the Milky Way would gradually fade as its existing stars burned out one by one. The interstellar medium is incredibly thin. In the regions between stars, there might be only one atom per cubic centimeter. By comparison, the air you're breathing right now has about 10 to the 19th power atoms per cubic centimeter. Even the best laboratory vacuums on Earth are far denser than most of interstellar space. Yet across the vast distances of the galaxy, even this thin material adds up. The interstellar medium accounts for about 10 to 15% of the visible mass in the galactic disk. This material is not uniformly distributed. Some regions are denser, forming the giant molecular clouds where stars are born. Other regions are extremely diffuse, heated to millions of degrees by supernova explosions. The interstellar medium exists in multiple phases simultaneously. There are cold molecular clouds at 10 to 20 degrees above absolute zero, warm neutral regions at several thousand degrees, warm ionized regions at 10,000 degrees, and hot ionized regions at millions of degrees. Each phase occupies a different volume and plays a different role in galactic ecology. Dust grains are a crucial component of the interstellar medium. These are tiny particles, typically less than 1 micrometer across, composed of carbon, silicon, ice, and other materials. Despite their small size, dust grains have an outsized influence on the galaxy. They absorb and scatter starlight, creating the dark lanes visible in images of the Milky Way. They also serve as surfaces where molecules can form. In the frigid conditions of space, atoms that collide rarely stick together, but when they land on a dust grain, they can bond and create molecules. The interstellar medium is where the galaxy's chemistry happens. Simple molecules like hydrogen gas and carbon monoxide are common, but astronomers have detected over 200 different molecular species in space, including water, ammonia, formaldehyde, and even amino acids, the building blocks of proteins. Some molecular clouds have complex organic chemistry occurring within them. Whether this chemistry played a role in the origin of life on Earth remains an open question, but it's clear that the raw materials for life exist throughout the galaxy. Supernova explosions play a critical role in shaping the interstellar medium. When a massive star explodes, it releases as much energy in a few weeks as our Sun will emit over its entire 10 billion year lifetime. This energy blows a bubble in the surrounding gas, creating a structure called a supernova remnant. The blast wave moves outward at thousands of kilometers per second, sweeping up and compressing the interstellar medium. These shock waves can trigger the collapse of nearby molecular clouds, initiating new rounds of star formation. The famous Crab Nebula is a supernova remnant, the scattered debris of a star that exploded in the year 1054. Chinese and Arab astronomers recorded seeing a new star appear in the sky, bright enough to be visible during the day for several weeks. Today, nearly 1,000 years later, the debris is still expanding outward, now spanning about 11 light years. At the center sits a pulsar, a rapidly spinning neutron star that emits beams of radiation like a lighthouse. Stellar winds also shape the interstellar medium. All stars emit streams of charged particles, similar to the solar wind that creates auroras on Earth. Massive stars have particularly powerful winds that can blow away surrounding gas, creating bubbles tens of light years across. When multiple massive stars form in the same region, their combined winds can evacuate enormous cavities in the interstellar medium. These structures eventually break open, allowing the hot gas inside to escape into the galactic halo, enriching it with heavy elements. The cycle of matter through the interstellar medium is one of the fundamental processes governing galactic evolution. Gas collapses to form stars. Stars fuse lighter elements into heavier ones. Some stars end their existence quietly, gently returning their outer layers to space. Others explode, violently ejecting their enriched material. This returned gas mixes with the existing interstellar medium, raising its metallicity, the astronomical term for the abundance of elements heavier than hydrogen and helium. Over billions of years, this process has gradually enriched the galaxy with the elements necessary for rocky planets and life. The Milky Way is not a closed system. Gas falls into the galaxy from the intergalactic medium, and gas is also expelled from the galaxy by supernovae and stellar winds. This exchange helps regulate star formation. If all the gas in the galaxy were converted into stars quickly, the Milky Way would have exhausted its fuel billions of years ago. Instead, the inflow of fresh gas and the recycling of material from dying stars has maintained a steady, if gradually declining, rate of star formation over cosmic time. Magnetic fields thread through the interstellar medium, though they are incredibly weak by terrestrial standards. These fields influence the motion of charged particles and play a role in the collapse of molecular clouds. Cosmic rays, high-energy particles accelerated by supernovae and other energetic processes, spiral along these magnetic field lines, spreading throughout the galaxy. When cosmic rays strike Earth's atmosphere, they create cascades of secondary particles that rain down on the surface. Some of these particles pass through your body right now, silent messengers from distant stellar cataclysms. The interstellar medium is also where we find some of the most beautiful structures in the galaxy. Emission nebulae glow in vivid colors as their gas is ionized by nearby hot stars. Reflection nebulae shine with a soft blue light, dust grains scattering the light of embedded stars. Dark nebulae appear as silhouettes against brighter backgrounds, dense clouds of dust that no light can penetrate. Each of these structures tells a story about the physical conditions in that part of space, the history of star formation, and the influence of nearby stars. Understanding the interstellar medium has been one of the great achievements of modern astronomy. A century ago, the space between stars was thought to be truly empty. Today we know it's a dynamic, complex environment, full of chemistry, physics, and beauty. It's the connective tissue of the galaxy, the medium through which matter flows from one generation of stars to the next, carrying with it the chemical legacy of billions of years of stellar evolution. And on that note, our journey through the Milky Way comes to a close. We've traveled from the supermassive black hole at the galactic center to the ancient stars in the halo, from the stellar nurseries where new suns are born to the inevitable future collision with Andromeda. The Milky Way is a place of constant change and unfathomable scale, yet it's also our home, the cosmic address where our story unfolds. Thank you for joining me on this relaxing voyage through the galaxy. I hope it brought you a sense of peace and wonder, whether you're drifting off to sleep or simply letting your mind wander among the stars. If you have thoughts or questions about tonight's journey, leave them in the comments below. And if you'd like more of these gentle explorations of the cosmos, consider subscribing to the Nocturnal Astronomer. Until next time, keep looking up.